Hello everyone, this is Vardman and welcome back. In our previous video, we have learned how to create a recurrence relation from a given function. So we will be solving recurrence relation in this video. So there are total 3 methods to solve a recurrence relation. First is substitution method, recursive tree method and master theorem. So in this video, we will be focusing on substitution method. Before we begin substitution method, let's see some useful formula that we are going to use throughout recurrence relation solving. So first one we have is sum of natural numbers. So if we sum of natural number, which is 1 plus 2 plus 3 up to n, then we have the formula which will equal to n into n plus 1 by 2. So here if we solve this, we will get n square plus n by 2, and we can write is asymptotically equal to big O of n square, because you can see the impact is only by n square. So this is the larger value if we take the value of n sum as larger number. So if we encounter this sequence, then we can write it as equal to big O of n square. Next is factorial, which is multiplication of numbers from 1 to n. So here we have 1 into 2 into 3 into 4 up to n. So this can be written as n factorial, and we have seen n factorial is nearly equal to n raised to the power n. So when we encounter a pattern like factorial, we can assume it equal to big O of n raised to the power n. Third one, here we have sum of square of natural numbers. So which is 1 square plus 2 square plus 3 square up to n square, and this is equal to n into n plus 1 into 2n plus 1 by 6. So if we solve this, so we will get is at n cube, so which is asymptotically equal to n cube, so we can write it as n cube. Fourth, we have GP series. So there are two types of GP series. One is increasing GP series, another is decreasing GP series. So in increasing GP series, we have 2 plus 2 square plus 2 cube plus 2 raised to the power 4 up to 2 raised to the power n minus 1. So this is increasing, and if you can see, this number is large. So if we take a value of n, which is a very large number, then these all will have no value if we compare it to 2 raised to the power n minus 1. So we can write it as big O of 2 raised to the power n minus 1. So in GP series, you can say the last term is the value. So in this we have 2 raised to the power n minus 1, so we can write it as big O of 2 raised to the power n. Other is decreasing series. So in decreasing series, you can see starting with 1 by 2, then 1 by 2 square, 1 by 2 cube, 1 by 2 h to the power n minus 1. So if you see, this is the only significant value, and if we compare these value, so it is decreasing. So 1 upon 2 square will be smaller than 1 upon 2, and 1 upon 2 cube will be smaller than 1 upon 2 square. So these all are decreasing, and if we compare the value of 1 by 2 and all other these, so they are very small as compared to 1 by 2. So we can write it as big O of 1. So decreasing series will be big O of 1, increasing series will be the last term of the series. Here in case which is 2 raised to the power n. Suppose you have a series like which is going 3 raised to 3 square, 3 raised to the power 3. So and last term will be 3 raised to the power n minus 1. So it will be big O of 3 raised to the power n. Now let's begin the first example. Here we have a recurrence relation, and we will be going to solve it using substitution method. So the relation is Tn, and the value of Tn equal to 1 when the value of n is equal to 1, and the value of Tn is equal to Tn minus 1 plus n if the value of n is greater than 1. Let's solve this using substitution method. So here we have our function Tn equal to Tn minus 1 plus n. So we need to find a value of Tn minus 1 and have to substitute in this position. So to get the value of t minus 1, let's discuss on it on side note. So we have Tn equal to Tn minus 1 plus n, and we have to find the value of Tn minus 1, which we are going to substitute here. So the value of Tn minus 1 will be, so for Tn we have Tn minus 1 plus n, So for tn minus 1, we will substitute the value of n as tn minus 1 here. So we will write t, substitute the value of n as n minus 1, n minus 1 minus 1 plus n. This n will be n minus 1 again. So we get the value of tn minus 1 as t n minus 2 minus 1 will become minus 2 plus n minus 1. So here we can substitute it. So tn will equal to, substitute the value of tn minus 1 here, which is t n minus 2 plus n minus 1. So this n will come as it is here, n. Now let's find the value of tn minus 2. So here we will write t n minus 2, which will equal to, substitute the value here. So t n minus 2 minus 1 plus n minus 2. We will have t n minus 3 plus n minus 2. So we will substitute here. So it will be equal to t n minus 3 plus n minus 2, and these will come as it is, plus n minus 1 plus n. You can observe a pattern here. So for first time we have n minus 1, for second we have n minus 2, for third we have n minus 3. So now suppose it is running for k times, so this will run k times. So we can write, we will get t n minus k. So for third time it is n minus 3, and for kth time it will be n minus k, and we can write everything else as n minus k minus 1. So here it was n minus 3, so we are getting n minus 2, so 1 less. So here it is writing k minus 1. Next will be n minus k minus 2, and this will be until n. We can see in the question the termination condition is when the value of n equal to 1, then the value will become 1. So here in other words it is t n equal to 1 if the value of n is equal to 1. So t of 1 is equal to 1. So this is the termination condition. And if you can see here, suppose this is getting terminated after k times. So in order to get it terminated, we need n minus k equal to 1. So this thing will become 1, then it will get terminate. So in this way we can find the value of k here. So k will be equal to n minus 1. So in order to get this terminated, we need the value of k as n minus 1. So let's substitute the value of k as n minus 1 and solve the recurrence relation further. So here we will have t. So instead of k, I will write n minus 1. And in the further equation, I will also substitute k as n minus 1. So here it will be n minus 1 minus 1. So I substituted n minus 1 as k here also. For the next also let's do the same, n minus 1 minus 2. So this will go until n. So here you can see this n minus n will become 0 and we will be only left with 1. So here we get t of 1 plus, let's solve it further, n minus, so this will be plus, so these two will become minus 2, so we can write it as plus 2 here. Next we will get here n minus, so this will become minus 3, and n minus 1 plus 3. This will go until n, and if we solve this, we will have t of 1 plus these will get cancelled. We will have 2 here, and this will also get cancelled. We will have 3 here, and this will go until n, and we have the value of t1 equal to 1. So this was the termination condition, so we can write it as 1 plus 2 plus 3 up to n. So this pattern is familiar. This is the sum of natural numbers, so we can write it as n into n plus 1 by 2, and if we solve it, it will get n square plus n by 2. So this can be written asymptotically equal to big O of n square, because n square is the major part here. If we take a value of n as some larger number, so this n by 2 will be very less as compared to n square. So we will have our final answer as big O of n square. We have our second question here, so let's see. So tn equal to 1 if the value of n is equal to 1, and we have tn equal to tn minus 1 plus log n if the value is greater than 1. So now let's solve it. So we will write the equation here. Tn equal to tn minus 1 plus log n. Now we have to substitute and find the value of tn minus 1. So let's substitute here itself. So we will have t n minus 1 plus log n minus 1 plus log n. So for tn we have log n here, so for tn minus 1 we will have log n minus 1. Let's solve it further. So this will become tn minus 2 plus log n minus 1 plus log n. Now we will substitute for n minus 2. So here we will get n minus 2 minus 1 plus log n minus 2, and other two things will come as it is, plus log n minus 1 plus log n. So here we will get t n minus 3 plus log n minus 2 plus log n minus 1 plus log n. Now suppose it runs for k times. So for first time we have the value as n minus 1, and for second we have n minus 2, for third we have n minus 3. So if it will run k time, then we will have n minus k here, and these will also change. It will have log n minus k minus 1, because here we have 3, so in log we have 3 minus 1, which is 2, plus log n minus k minus 2. This will go up to log n. Let's see what we have after k iteration. So we have t n minus k, and our termination condition is 1, so n should be equal to 1. So t1 is our termination condition, which is 1. So to make this termination happen, so we need the value of n minus k equal to 1. So let's solve this. So to make n minus k equal to 1, we have to write n minus k equal to 1, and from here we can find the value of k, which will be equal to n minus 1. So let's substitute it here. So we will have t and substitute the value of k here, plus log n minus, it will come n minus 1 minus 1 plus log n minus 1 minus 2. This will run up to log n times. Here this will become 1. N minus n is 0 and 1 will be left. This will become 1. We got our termination condition here, plus log. So this we will solve and we will get it as n minus n plus 2. This will become log n minus n plus 3, and this will be up to log n. If we further solve this, so tn, the value of t1 is 1, plus this will become log 2, and this will become log 3, and this will up to log n. So if you can see, there is a formula for log. So if we have log a plus log b plus log c, so this can be written as log a into b into c. So we will use this formula here. So we have our similar pattern here. You can see we have log 1 plus log 3. This will run up to log n. This can be written as log. So this summation will turn into multiplication. Log 2 into log 3 into log 4 up to log n. So we will write this. So you can see this inside the log. This is the pattern for factorial. So if we write 1 dot here, so this will not change, but it will be a factorial pattern. So this can be done as n factorial, and you know n factorial is nearly equal to n raised to the power n. It will become n raised to the power n, and we will have our time complexity as log n raised to the power n, and we can further solve this. So by applying the log formula, the n will come in front and we will have log n as it is. So this, the final time complexity for this question will be big of n log n.